Welcome back everybody. So as I promised, now we're gonna determine where the flow is turbulent, laminar, or transition. Okay, so what tools will we use? We will use table 4.1 page 196 to verify. Okay, so how does this work? First, we will assume the flow type. Okay, then we will find the Reynolds number. If the Reynolds number falls within the accurate interval, our assumption is correct. Okay, what does it mean? The first thing I will assume, so I will start with assumption. I will say, oh, this is turbulent flow, laminar flow. And then later, if my Reynolds number falls within the range, it means that my assumption is correct. So, which means that I know the equation to use. Okay? Now, let's start. Now I'm gonna assume this is, I'll use green, turbulent flow. Okay, so what happened? Look at the table. You see the track coefficient is equal to 0.44. Okay, so what happened? So the Reynolds number you can calculate is equal to square root of 9.38 over track coefficient, which is 4.617. Okay, is 4.67 less than 2 to the power of 5, 2 times 10 to the power of 5, and greater than 10 to the power of 3? No. Right? I'll put a big X here. No. So, this is not turbulent flow. Okay? Similarly, I'm going to assume this is transition flow. Okay, my bad. Let me do this. Transition. Sorry, guys. Put transition. So what happened if transition flow? So the equation we get is track coefficient equal to 18 times Reynolds number to the power of negative 0.6. Okay, so now you have this equation right here. Okay, so you can replace the track coefficient. Let me see. You can replace the track coefficient with 9.38 over RE square. Right? Okay. Equal to 18 times Reynolds number to negative 0.6. Okay. And then if you time RE square both sides, you get this. RE to the power of 1.4. So you get Reynolds number equal to 0.521. Now, is 0.521 greater than 1 and less than 10 to the power 3? No, because 0.5 is less than 1, right? So this is false. So you say this is not transition flow. Okay. Now, lastly but not least, you assume laminar flow. Guys, if this is the case, if you don't have time, you can directly say this is laminar flow. Okay. On the exam, but I'll show you the complete reasoning. So I would say, because if it's not turbulent or it's not transition, it will be laminar. However, let's do it step by step. So I will assume this is laminar flow. Okay, now what happened if it's laminar flow? Your drag coefficient, you're going to use this equation, drag coefficient equal to 24 over Reynolds number, right? And you're going to replace, the drag coefficient 3.98 over RE squared equal 24 over RE. You time both sides by RE squared, 9.38 equal 24 times Reynolds number. Okay, you're going to get Reynolds number equal to 0.39. Okay, all you need to do is you're gonna check if 0.39 less than 1. Yes, it does. Let me put this blue. Yes. So, outflow is laminar. Perfect, perfect. So the Reynolds number makes sense. We confirmed outflow is laminar. And then what? How can we find UT? How can we find the terminal? Because remember outgoing. You have to remember outgoing. Remember outgoing. Let me check the time. Okay, perfect. Terminal. Velocity. Okay, that's the goal. Now we know it's laminar flow. So what can we do? We will solve on of the missing variables. Okay, we know that this is laminar flow, so we can use this equation. We can use drag force equal 24 over Reynolds number. Okay, now let's solve for CD. Okay, remember we have that we use this equation. Let me do this equation 1. So using equation 1, using equation 1, you have let me solve for drag coefficient. Reynolds number, you can okay, let me see how to solve it. Okay, so CD equal 24 over Reynolds, so you can write Reynolds equal 24 over CD. Okay, equation 1, say Reynolds square times CD equal to 9.38. So this equation right here, you can say 24 over CD square times CD equal 9.38, right? So you can say 24 square over CD equal 9.38, and you can get the drag coefficient to be 61.4072. Reynolds number, did we have it? Yes, we do. In fact, we don't need it because we have all the variables and we need already. Okay. Lastly but not least, let's finalize UT. Okay, let's find UT now. Remember UT. Let me see, what is UT? Let me copy that formula for y'all. What is UT? Where's that beautiful formula? Ah, there we go. UT, we're going to use this equation right here. So let me write down again for you. UT equal to square root of 4/3 times diameter times rho S minus rho F times G over CD times rho F. Okay, perfect. So we plug in a number, 4/3 times diameter is 10 to the -3, rho S minus rho F. Rho S is the speed density, 7,870 minus 1,052 times 9.81 for the gravitational constant. CD, drag coefficient, we just calculated 61 times 4072, and then our fluid density to be 1,052. So you arrive at 0.072 meter per second as your answer, and you convert it to centimeter per second by times 100 centimeters per 1 meters, and you get 3.72 centimeter per second as your final answer. Okay, thank you everyone for your attention, and that is how you solve for terminal velocity for this particular problems.